Last week we talked a little bit about some different kinds of pollutants, and we talked generally about what some of them do in the environment, but we're going to spend some more time talking about pollutants in general and what kinds of interactions they can have in our environment. So this is based on Chapter 7 in the Environmental Chemistry book, where he describes what happens to organic compounds in the environment, but there's no reason we can't look at pollutants more broadly as well, and I think that this is worth it. So what we need to pay attention to is that there are four main areas of interaction for pollutants in our environment. And so we're going to look at these four areas. So the first one is the air-water interface. And at the air-water interface, the materials that are going to move between air and water, this mainly is dependent on the solubility and on the vapor pressure. So our next interface is the water-soil interface. And this also depends on solubility. And it also depends on how well the materials, the pollutants, are going to adsorb, stick on, to the soil particles. So we also have the soil-air interface, and this is going to be due to adsorption, just like we said a minute ago, and also vapor pressure, because everything having to do with gases has to do with vapor pressure. And then our fourth area is really any phase, so air, water, or soil, with living organisms. And this is a pretty complicated interaction. So this relates to our exposure level. This relates to their solubility in water, because our bodies are, pretty fully aqueous systems, but also in our fatty layers. And these are going to get pretty complicated, so we aren't going to get very far into it, but we'll at least make a start. So as you may have noticed in my four main areas here, there are several areas of chemistry that we need to identify so that we can understand the different topics that we're looking at. So solubility is one of them. Vapor pressure is another one. Adsorption is another one. We have solubility of gases, and we have solubility of liquids and solids. And then we have vapor pressure, we already mentioned that one, and absorption. And we also need to pay attention to solubility in living organisms, and along with that, bioaccumulation. So what kind of factors affect whether or not materials stay in the body for a long period of time. So if we look at all of these different pieces, there's actually a couple more that I haven't mentioned, but we'll get into them a little bit later. Let's go ahead and take some of these concepts one at a time. All of these are ones that we've talked about in other classes, and so you have a foundational knowledge of different things like solubility and vapor pressure. You may or may not have talked about what adsorption is, but we can boil these down to their chemistry fundamentals, and that's where we're going to start. So in this video, I'm going to take a little bit of time and we're going to talk about solubility. This is sort of one of the most fundamental of the concepts. So I want to spend some good time. So solubility has a lot to do with intermolecular forces. And these intermolecular forces, or IMFs as I'm going to use, have to do with what kind of bonding we have going on in our materials. Now, our two main types of bonding that you've probably talked about before are ionic and covalent. And you probably have identified that if you have an ionic compound, your short way of thinking about this may have been that you have a metal cation and a non-metal anion. And that's pretty good. There are one or two non-metallic cations, but for a short, summary, this one is really helpful. For covalent compounds, these are almost completely non-metal elements. And of course, we have at our boundary, sort of between these, we have acids and bases, many of which are covalent compounds that still make cations. So anyway, we have to kind of pay attention to those as special cases of both of these, but we're going to go ahead and stick with these classifications so that we can kind of talk about what these systems are like. All right, so before we get too far into our solubility and our bonding and what kind of materials we have, we also just need to talk about what a solution is. So a solution is made out of a solute and a solvent. And the only thing that distinguishes these from each other is that the solute, and you can have more than one, is the minority component in your mixture. And your solvent is the majority component. So you can have only one solvent. You can have only one thing that's in the majority. But you can have multiple solutes in your solvent. So in our solution, one of the things that we need to pay attention to when we talk about solutions is that all phases are possible here. So mostly we are trained to think about aqueous solutions, but in reality we can have gaseous solutions. Air is a great example of a gaseous solution. If we think about what air is like, we know it's got nitrogen gas, oxygen gas, argon, carbon dioxide, water molecules, all kinds of different gaseous components. But only one of them is the majority, and we know that that one is nitrogen. So nitrogen gas is the solvent in air. And all of the other gases that are present in the air, those are all solutes. That they are dissolved in the nitrogen majority. You can also have lots and lots of different liquids. Of course, we're used to thinking about water solutions, water-based solutions, because those are our most common ones that we pay attention to. So, we can look at salt water as a great example. You can have your coffee or tea. These are water-based solutions. Lots and lots of different examples. Beer, alcohol. These are solvents that are still dissolved in water as the majority component. But then you can also have, gasoline. Right? Gasoline is a complex mixture, and it has an organic solvent. I don't actually know which particular one it is, but we have a bunch of different, it's probably proprietary anyway, we have a bunch of different organic molecules that are present in gasoline. But you can also have a solid solution. And this one is probably the one we think of the least, because it's just not very familiar to us. But if we think about something like steel, steel is a solid solution that is made up of mostly iron, but it has some carbon, it's got some oxygen, it's got a whole bunch of minority components in here that affect the specific properties of the steel. So depending on whether you have something that's galvanized, it might have some zinc in it, it might have some molybdenum in it. All of those different minority components change the properties of the steel. And so you can have things like stainless steel that are resisting rust, and that's because of some of the minority components in there. But you can also have dirt. If you just think about what soil is like, it is a heterogeneous mixture or a solution, geneous. And depending on where you are, the makeup of that dirt or soil is going to be quite varied. And we've started looking at some different soils I have a couple of websites linked to our Moodle for this week for us to learn a little bit about some of the soil basics. And in the soil lab that you're doing, you can also see some different examples of soils. And you can see that they are pretty heterogeneous. And by heterogeneous, we mean that any kind of a heterogeneous solution means that it's not identical throughout. So if I look at one part of a sample, it could be slightly or really significantly different to the rest of the parts. But a homogeneous solution, it doesn't matter which part of it you sample, all of its properties are going to be the same. Anytime we make a solution, the solvent particles are being surrounded by the solvent, solute. Solute particles are surrounded by the solvent particles. And one of the easiest ways for us to think about that is in a water sample, where I have some solute particles and then I have water molecules that are surrounding it. I should probably use a different color. So all of these solute particles, regardless of what they are going to be surrounded by our solvent particles. And that is what it means for something to be dissolved. So if our particles are not dissolved, then they are insoluble. So when we look at our solubility of our materials, we can look at solubility based on the sort of short idea of like dissolves like, which you've probably heard before. And when people use this little shorthand reminder, they're usually talking about intermolecular forces. And what is at the heart of all intermolecular forces is Coulomb's law. Coulomb's law tells us that how strongly we have two materials that are either attracting each other or repelling each other is based on two pieces. One of them is the size of the charge, and the other one is the distance between those two charged particles. So that means that the stronger force is due to larger charges and or particles being closer together. All right. Now, you don't have to pay attention too much to the equation here because I'm never going to hold you responsible for remembering it. I just want you to remember that this force of attraction is higher for larger charges and also larger for smaller distances away from each other. So just those two conceptual ideas. The closer that two things are, the more they can interact with each other. So that just kind of makes sense. And then the larger the charges, this also makes sense that we would have a stronger attraction if the two particles are oppositely charged, or a stronger repulsion if they happen to have the same charge. So when we are looking at the charges on the particles, then we have to pay attention to whether or not our particles are ionic or covalent. Because the size of the charges are directly related to whether or not a material is ionic or covalent. So ionic particles, we know, make full cations and anions. So if I think about a material like calcium nitrate, this, I know, this is a metal, and if I look at the periodic table, I can see that this is going to be a calcium 2+, and then nitrate, I remember from my list of different anions that this is nitrate with a -1 charge. And so this has a full 2+ charge on that cation, on that calcium, and this nitrate has a full minus charge on it. And that's a little bit different from our covalent molecules. So if we think about a covalent molecule like CH2Cl2, one of our chlorofluorocarbons, right? We can draw a Lewis dot structure for it. And we can recognize that our carbon-chlorine bonds are going to be polar bonds. So the chlorine is more electronegative than the carbon, and so it's going to pull the charge more strongly onto the chlorine. And we're going to have these partial negative charges on the chlorine and the partial positive charges on the carbon. The carbon-hydrogen bond has a very small electronegativity difference. So overall, we're just going to see that this part of the molecule is going to have a partial positive charge, and then these two parts of the molecule are going to have partial negative charges. But this partial charge thing, that means that it is less than 1. Okay? It is not the same as a -1 charge. It is less than that. So when we look at the strength of the interaction between these two, we can see that ionic charges, because they are full positive and negative, these are going to be stronger. So my ionic bonds are stronger than covalent bonds in general. We might have a couple of exceptions. But in general, our ionic interactions are going to be stronger than the covalent bonds because, or our covalent interactions, because of that full positive, full negative charge compared to the partial positive and partial negative charge on those covalent ones. So when I have a compound that is covalent, that has a partial positive and a partial negative, I call this a polar covalent compound. And the like dissolves like idea means that polar solvents are going to dissolve polar solutes. And the same is true for nonpolar. That nonpolar solvents will dissolve nonpolar solutes. But The truth is that polar solvents also sometimes dissolve some ionic compounds. And what happens when we dissolve those ionic compounds is that even though that ionic bond is really strong, when we dissolve an ionic compound, in this case, the ionic compound dissociates. So let's illustrate that. On the left, we have a picture of an ionic compound that's being dissolved. You can see that this ionic solid has alternating positive and negative charges. And when those positive cations dissolve, they are going to be associating with the oxygen part of the water molecule. That's these little white and red guys. And then this anion is going to associate with the positive partial charge on the hydrogens of the water molecules. Compare that to a covalent compound that happens to be polar, so it has a partial positive and a partial negative charge. And in the partial positive side of the molecule, that will associate with the oxygens for the water. And on the partial negative side of this covalent compound, that will also associate with the hydrogens on the water. So we always have attraction taking place where our positive parts of either our molecule or our cations are going to be associating with the oxygen on the water, and the negative parts of our molecule or our anion are going to associate with the hydrogens on this compound. I want you to specifically notice that this ionic compound is dissociating. The positive and the negative parts of this solid are getting dissociated from each other and associating with the water molecules, which will then surround it. In this covalent compound, though, those molecule parts do not dissociate from each other. Each molecule stays intact and is still surrounded by its solvent particles. So hopefully you are remembering all of the details about figuring out what compounds are polar. If you need a little review on this, I can recommend some pages out of the OpenStax textbook, which is a general chemistry textbook that's freely available to anybody. So just let me know if you need a little reminder about solubility rules or about how to figure out polarity. If I have a chance, I'll make a review video on it, but I don't know if I'll have time for that. So I'll go ahead and add some homework problems that hopefully should be pretty basic. They're just reminding us of solubility and how to look at compounds and figure out whether or not they're polar and so on.